Flight began as a contradiction. We studied the precise aerodynamics of birds and built delicate wings, but we relied on heavy, fragile piston engines to claw through the air. For the first few decades, the propeller defined the early age of aviation. But as military and commercial demands pushed for higher altitudes and faster routes, the propeller encountered an unavoidable ceiling. This animation illustrates the aerodynamic anomaly at high velocities. As the aircraft pushes faster, the rotating propeller blades stop acting like simple air movers. Instead, they become obstacles, violently cutting through their own shockwaves. Furthermore, the internal combustion engines driving those blades depended entirely on reciprocating motion, pistons rapidly pumping up and down. That mechanical movement introduced severe vibration, metal fatigue, and massive energy loss, exactly when peak efficiency was required. These engineers were colliding with the absolute limits of classical aerodynamics. By the 1930s, two parallel lines of investigation emerged across Britain and Germany. Instead of trying to spin a propeller faster, a few engineers started asking a radical question. What would happen if you accelerated air continuously with no mechanical rotation at the front at all? Frank Whittle, an engineer with the Royal Air Force, formally patented a concept in 1930. He treated the engine as a hollow system that ingested air, burned fuel, and expelled high-energy exhaust directly backward to create thrust. At almost the exact same time, German physicist Hans von Ohain was independently drafting similar blueprints, driven by the exact same mathematical frustrations with propeller physics. The philosophical shift was complete. Forward motion would no longer rely on external blades chopping through the sky. Thrust would come from taking air inside a machine, burning it, and shooting it directly out the back. The core science driving this relies on a simple rule, Newton's third law. If you violently accelerate mass backward, you move forward. This outlines the continuous flow cycle. Multi-stage compressors draw ambient air inside, rapidly squeezing it into a pressurized space. Mixed with fuel, it burns continuously. The rushing exhaust passes through a rear turbine, extracting kinetic energy to keep the front compressor spinning. Building this cycle created immediate mechanical nightmares. If the compressor stalled, the airflow violently separated inside the engine. If the continuous flame fluctuated, it created destructive oscillations that could rip the metal casing apart. The physics of direct thrust were elegant on paper. In practice, building a jet engine required containing a highly unstable, continuous explosion. The urgency of the Second World War quickly forced these unstable designs into the sky. In Britain, Whittle's engine concept powered the Gloucester E-28/39, shown here on the airfield. Its flights proved the structural viability of the concept. Meanwhile, Germany pushed the Messerschmitt Me-262 into operational service. It immediately secured a decisive speed advantage over every existing propeller-driven aircraft in the war. Yet both nations encountered a severe mechanical flaw. The engines successfully generated massive thrust, but their operational lifespans were disastrously short, often failing completely after just tens of hours of use. The standard steel alloys of the era softened under the intense heat of combustion. The fierce thermal gradients inside the engine caused microscopic cracks to propagate rapidly through the spinning rear turbine blades. The jet engine solved high-speed flight, but the extreme temperatures destroyed the machine in the process. Its endurance was strictly unsustainable. In the years following the war, post-war analysis at firms like Rolls-Royce and General Electric forced a shift in priorities. Engineers analyzing internal cutaways like this one began focusing on building systems capable of surviving the heat they generated. The breakthrough arrived through material science. Metallurgists developed nickel-based superalloys that maintained strict rigidity even when subjected to extreme temperatures that would melt conventional steel. Investment casting formed components with complex internal geometry. This cross-section reveals hollow passages flowing cooling air inside the spinning blades. Wrapping the exterior in a cooler air film allows turbines to safely operate in environments hotter than their physical melting point. Propulsion engineering became a highly sophisticated system of controlled failure management. As technology scaled into commercial aviation, like this Pan Am Boeing 707, new operational constraints appeared. Airlines required strict fuel efficiency to survive economically, and cities demanded heavy reductions in noise pollution. The engineering solution to these economic and regulatory barriers was the high-bypass turbofan engine. Instead of forcing all ingested air through the hot combustion core, a massive front fan redirects the vast majority of air completely around it. This slower, cooler bypass air drastically increases fuel efficiency while acting as an acoustic dampener to muffle the roaring exhaust. The turbofan evolved the engine from a raw thrust generator into a carefully balanced thermodynamic ecosystem. The resulting collapse of distance altered daily life. Routes that previously required weeks on ocean liners were reduced to a matter of hours, reflected here in the bustling departure boards of mid-century airport terminals. Global trade networks expanded at unprecedented rates. Physical distance ceased to function as a strict temporal barrier to commerce or logistics. National economies and military strategies reorganized around the assumption that an aircraft could connect any two major cities on Earth within a single day. Mastering the continuous explosion removed distance as a temporal barrier to commerce and connection. Today, engineers assembling the newest jet propulsion systems are once again scraping against absolute physical limits. They're constrained by maximum turbine temperatures, finite fuel reserves, and strict climate emissions regulations. To push past this wall, the industry is testing ceramic matrix composites that resist intense heat and exploring hybrid electric architectures to offset traditional combustion. Every single innovation serves the exact same objective: extracting maximum energy from tightly controlled combustion without vaporizing the machine built to contain it. Humanity has long since solved the contradiction of sustained high-speed flight, but the history of the jet engine reveals an inescapable reality of engineering. Every physical solution simply exposes a new boundary, and every boundary demands an entirely new form of science.